and welcome to Smoothing the Gap between NP and EDR. My name is Tilman Milso, or just Til. I'm from Utrecht University, and this is joint work with Jeff Erickson from Champaign, Illinois, and Ivo van der Hoog, who's also from Utrecht University. Okay, before I can tell you about smoothing the gap between NP and EDR, I need to take a detour and need to talk with you about the model of computation that we consider in that talk. So let me start with a standard model of computation. Namely the word RAM, random access machine. It consists of a central processing unit, a set of instructions, a pointer which tells us now do this instruction, it tells us which instruction we are currently on, and an infinite array of memory cells. The central processing unit does whatever the instruction tells it to do, and it operates on the memory cells. So it reads and writes on the memory cells. The memory cells are also used to reference to other memory cells. And in this way, the word RAM is operating. I want to point out to you that there are some subtleties with this model of computation that you're all well aware of, and that's precision. So how many bits can a memory cell store? If a memory cell stores a constant number of bits or too few bits, then we cannot address all the memory cells that we do need. So we need at least log n number of bits per memory cell. But in case that a memory cell would be allowed to store an arbitrarily large number of bits, and then what we could do is we could add two numbers that would be counted as one operation, but it would be kind of cheating because we do a huge number of bit operations at the same time. So we could kind of cheat and abuse this and then solve problems faster, like problems that we believe are only solvable in exponential time in polynomial time. So that we don't want. So there's this issue, but we know how to solve it. We just have to make some restrictions of the range that the word size is. But there is another set of limitations also related to precision, namely the world that we live in is inherently continuous, right? So it's not discrete, but in the word RAM we can work with discrete stuff because we have only bits that we interpret as integers. And this can be seen or is very obvious in computational geometry because the main object that we work with is points in the plane. And points in the plane are inherently continuous. But also in other parts of theoretical computer science, we work with continuity. For instance, there are lots of papers talking about some Gaussian noise, but really, if you then want to have your input where you added some Gaussian noise run on word RAM, no, that's not going to work, right? Because you can't even put it into the word RAM. You can't have it as an input. So what we do in computational geometry is we extend the word RAM model and to include also an infinite array of real inputs, and now we call the real RAM, random access machine, model of computation. So that's our main hero of this talk that we're going to work with in this talk, the real RAM, random access machine. But there are some issues. There is this anti-hero, the Joker, who was hiding a bomb in the real RAM. So remember that the real RAM works with infinite precision. And I told you with the word RAM, we don't want to allow it to work with infinite precision. And actually, if you allow the rounding operation, then it's possible to abuse this infinite precision. And you can solve p-space complete problems in polynomial time on the real RAM. That's not good. That's what we think is way too powerful. We don't want our model of computation to be that powerful. That kind of contradicts our belief in these complexity classes. And then the natural way to go about it is just we disallow or forbid all more complicated types of operations like rounding, sinus, cosinus, exponential function, logarithms, or whatever thing you could think of to have access to the bit representation of the real number. But it could still be that the Joker has another bomb hiding in the real RAM, and somehow it could be abused that we have this infinite precision, and with this abuse you could do something else that we don't really want this model to be able to do. And this is like our first result. We kind of try to put the Joker at least partially behind bars and try to prevent this. And this will lead up later to other results that I'm going to tell you about. So what's the idea here? Okay, so imagine you have an algorithm that works on the real RAM, and now I could also make it work on the word RAM. That'd be great, right? Because we trust the word RAM. Word RAM really trusts with real RAM. Kind of suspicious. Okay, and that's what we want to do. And what we have to first think about is if you have some real input, you have to make some integer input out of this. And that's not trivial because, you can't just do this, right? There are more real numbers than there are integer numbers. So we do this in two steps. First is we add some random noise. And for the rest of the talk, whenever I say random noise, this model of perturbation is we have it uniformly distributed for every real input variable, and we denote by delta, like by how far we are perturbing to the left and right. So like that's the size of our interval by which we can perturb. So I have some real number, we take some interval around it of length delta, and then we find a new number within that interval uniformly distributed, and that we do for every real input. And so if you're not familiar with smooth analysis, so this is a little bit going to smooth analysis, then maybe check out some videos on YouTube to learn about it. Or for now, just go with that this is a kind of established way in theoretical computer science to deal with worst case inputs. A different type of analysis next to worst case analysis. Okay. And then as a second step, we just do roundings. That obviously we have to do that in order to get discrete input, and then we somehow fill this into a representation using integers. And the rounding gonna be more fine than the amount of perturbation that we have. Okay, so now the question is, why does it work? But more importantly, what does it even mean that it works? So for that, I want to have a closer look at the real RAM model again. Namely, I want to look at the types of instruction that we have. And what is important is there's only one type of instruction where we branch. So imagine an algorithm where we have two different answers, either yes or no. And imagine in every comparison operation, we would get the same result. So we have two inputs, and we do some computations, and at each step we get the same comparison, and the pointer will always be at the same place. And that also means that both of these inputs will yield the same result. Okay, so that is what we mean with two inputs being equivalent. The second thing you want to notice is that every register, every memory cell, the content of that memory cell is some function of the input. To be more precise, it is a rational function, means this is a fraction of two polynomials. But just think of it as being one polynomial. Okay, that just makes our life a little bit easier to talk about it. So we have one polynomial, and then we compare this from that input, whether this is larger than 0 or not. But really what we're doing is we're having these two types of inputs. We have the input with Gaussian noise and the rounded one. And what we do have to show is that this rounding does not change the result in any of our computation steps. Okay, so this is our first theorem. So if the algorithm is tame, so that means the polynomial that we talked about, this p, in every step, whenever we do a comparison, has a bounded number of variables and a bounded total degree. So those two conditions, which for a majority of algorithms in computational geometry is actually true. We point out there are some examples where this is not true, but for the majority of algorithms in computational geometry, that is true. And then what we get is that we can then run that same algorithm on the word RAM with bounded precision. And we could just round everything. And that makes it very nice to us. So an example which we don't capture is you've given us input and numbers, you add them up, you want to know whether it's larger than 0. That's kind of a really stupid question, but our theorem would not handle it. I think there should be easy proof for it. I think we made an easy proof for it, but that's not part of our framework. Okay, so this is our first main contribution. It's more of a philosophical result, which puts the Joker behind bars. But now we're ready to introduce to you our next results, which will use Theorem 1 and the definition of the real RAM that you just learned about. Okay, so in the title you heard about this smoothing the gap between NP and ETR. So now I want to tell you, what is this complexity class ETR? Okay, so the same way that you could define NP in terms of satisfiability, ETR could be defined in terms of ETR, which stands for existential theory of the reals. The complexity class and the problem that defines this are named the same. We have different symbols for them, but we give them the same name. But I want to give you a different way to think about the complexity class ETR, because it's kind of tedious to define this existential theory of the reals. So let's look at NP again, and a different way to look at NP is you have your crystal ball, and you're guessing some solution for your input, and then you check it on the word RAM whether that solution was actually correct or not. Now, ETR could be defined in an analogous way, namely we look into our crystal ball, but we guess real numbers, and then we check it on the real RAM. So instead of word RAM, we use a real RAM. And that's our second main contribution, namely we showed that this is an equivalent different way of defining ETR. We also give some applications to this. And again, it's more of a philosophical result, so that we have a different way of thinking about this complexity class ETR. Okay, so now you know the definition of ETR. Let me tell you a few more basic facts about it. Okay, so it is contained in NP. Sorry, it contains NP. This is trivially true because the word RAM is like a submodel of the real RAM. The real RAM is just more powerful than the word RAM, so that's easy. So then ETR is contained inside P space, and that's just someone called Kenny came up with a very sophisticated algorithm using algebraic methods, and then other people did similar algorithms, and these algorithms could be shown to be in P space, but they're more of a theoretical type of algorithms. You don't really want to implement them in practice. But this shows P space membership, which is non-trivial. Okay, one important thing you should know about ETR complete problems, and that's maybe also a big motivation for this work, is that all the methods that we have that work for NP, they stop working for ETR complete problems. So consider traveling salesman problem. We're capable of solving it for 10,000 of cities, but for ETR complete problems, we cannot give even exact solutions, often for very, very small instances. and not even that we don't have an efficient algorithm for it. It's like, even if I tell you have a 1 year of time and just try everything, and people really care for just trying to solve some small instances just to see how far they can push it, and they cannot. So you should really care about the difference between NP and ETR. A next thing that I want to point out is that there are a lot of important problems that are ETR complete. One is packing geometric objects into a geometric container. Here we don't want to have any objects to overlap. We want every object to be inside. And let's say we allow rotations and translations. So already for 11 unit squares inside a square, we don't know what is the optimal way of packing this. If you want to know more about packing, check out my other video. Another famous problem in computational geometry is the art gallery problem. Here we've given a gallery. A gallery is symbolized or modeled by a simple polygon in the plane. Every guard is modeled as a point, so we try to guard the gallery. And we want to place as few as possible inside the gallery such that everything is guarded. And we say a point guards another point if the line segment between them is fully contained inside the polygon. This is another famous problem in computational geometry. And I also want to say that the complexity class ETR is more important for computational geometry than maybe for other fields of theoretical computer science. But there are also problems outside of theoretical computer science which are ETR complete, and one of the first which has been discovered was finding a Nash equilibrium, a mixed Nash equilibrium of at least 3 players. Okay, that was it. I want to now, so you see there is a lot of relevant problems that we care about are ETR complete. So it's not just, this made-up complexity class about this weird type of problems. Actual problems that we care about are complete for that complexity class. I want to now narrow it down on a specific subset of ETR complete problems, so-called recognition problems. So if we've given a set of disks, as you can see here, then what we can do is we can make a disk intersection graph out of this. Okay, that we can solve on the real RAM in polynomial time very easily. But now the recognition problem asks you, given a graph, find those disks. Okay, and this problem is ETR complete for various types of geometric problems. So you could do the same with segments, rays, line arrangements, name it, it's probably ETR complete. So there's a huge bunch of these recognition problems which are well studied in computational geometry. And you could ask, is it in NP? And so no, we by now know it's not. But there's maybe next to ETR completeness, maybe the way to think about it is the reason that it's not in NP is because if I want to describe those disks, we know there are lots of examples where you need an exponential number of bits in order to describe the disks. Okay. So that means you need some fundamentally different way of describing the disk if you want to hope for NP membership. So that is what we call the gap between NP and ETR. So it's a little bit of a fire there. So we have all these instances which need an exponential number of bits, or which need algebraic numbers in order to be solved. And now using smoothed analysis, we're smoothing the gap between NP and ETR. We can extinguish many of those fires, specifically for recognition problems, which are a majority of the known ETR complete problems. And I want to show it to you on the example of the disk intersection graphs. So imagine we have one of these poisonous graphs, and we want to find a disk intersection graph. So this is our problem. Okay. So we know that there is a representation of it, but it does need exponential precision. So we kind of guess that one, we know it exists. And what we do then is we add some uniformly distributed noise. And you know from theorem one, what we talked about earlier in this talk, that now we only need a logarithmic number of bits to describe this disk intersection graph without changing the underlying graph. So I take these disks, I perturb them a little bit, and I can snap them. I still have disk. I still have the same disk intersection graph, so combinatorially nothing changed. But now they're much easier to describe. So we know this because of theorem one, because these tameness conditions are really met here. And then we get this graph, and this graph is safe, and it has this low complexity. So one way to think about it is, so you have a graph, and smooth analysis is we're looking at a neighborhood of this graph. But now, in order to say when are two graphs close to each other, we are not saying this in terms of graphs. We're not describing proximity in terms of graphs, but in terms of disks. And that makes sense because we think of this graph as coming from disks. We are doing geometry. So we say two graphs are close if they have kind of two representations which are close as disk intersection graph representations. Like, if you take like their Hausdorff distance pairwise between these vertices, for instance. So this is our third and last main contribution. So we show if we have a problem which is tame, so that means that so a recognition problem, so this is specifically for recognition problems, and we know that every checking or doing all the comparison operations that we're going to do in checking if the solution is correct can be done such that the polynomials that we have there are with bounded number of variables and with bounded total degree. Then we know using smooth analysis that the instance that we get on average need low complexity. So we say we're like safe instances. And you can see, for instance, for disk intersection graphs, so you only need to share pairs of disks. So that would only use 6 variables, 2 for the center point, 1 for the radius, and only degree 2 polynomials, which again is very nice. Okay, that was our last contribution. I thank you for your attention. Please also come to the live talk. Please also come to the poster session if you like it, or if you want to know more about it, ask more detailed questions. Yeah, thank you for your attention.